And let's just have a look at the geological processes that we just can conclude from looking at this photograph. We see here a pluton. Once has it intruded a older host rock. So these dark gray rocks, they must be older. They might be metamorphic rocks, for instance, or perhaps sedimentary rocks. We cannot see that from this distance. But clearly this pluton must have released some heat into this country rock. And here we can assume that nearby the contact, where the temperature was strongly increasing, that here we are producing some contact metamorphism at the top and at the bottom of these plutons. Clearly lots of material got eroded, not only the several kilometers of material that were overlying this magma chamber at the stage of intrusion, at the time of intrusion, also all the material here that now separates these two granite bodies from each other. So this valley here clearly was eroded and was cut into by usually water action and physical weathering and erosion. And this material was transported downwards into river systems, and along the rivers material was taken out. So you can imagine how long it might have taken to remove the several kilometers of rocks above and all the rocks that actually were once producing here a uniform magma chamber with a top and a bottom. Yeah, to carve all these valleys and irregularities into this landscape, to form it to the shape that we see today, must have taken a lot of erosion, a lot of time, and a lot of transport was necessary to move all this material away from its original site into the next sedimentary basin, where it still might sit and might form new sedimentary units and sequences, and in the future sedimentary rocks. From these processes that we just have seen, from intrusion, magmatic processes, metamorphic processes, exhumation, weathering, erosion, sediment transport, we can see that rocks have actually a long history. And this history relates to the formation of these different types of rocks, of sedimentary rocks that are dependent on erosion and the availability of a transport mechanism that brings sedimentary material into a sedimentary basin. Burial and heating that converts such sedimentary rocks into metamorphic rocks, and increasing temperature that might provide melting or partial melting of such rocks, which then subsequently forms igneous rocks. Such igneous rocks again can be brought to the surface and undergo erosion and form then new sedimentary layers or rocks somewhere in the next sedimentary basin. We also can take shortcuts. We might have igneous rocks that are getting further buried and then convert into metamorphic rocks. Such metamorphic rocks might then go to the surface, get eroded, redeposited in a sedimentary environment, or even such sedimentary rocks without ever getting buried or partially molten, they might be eroded and redeposited as younger, newer sediments in other sedimentary basins. Also, metamorphic rocks might undergo polyphase metamorphism. Temperature in a metamorphic rock might decrease and then increase again, and a second cycle of metamorphism gets overprinted or on these rocks, and new metamorphic minerals form. Such metamorphic minerals might then give evidence of a cyclic, repeated heating and cooling of a metamorphic rock. Also, we have interaction with the mantle. All this here, this cycle of rocks is looking only at processes in the crust or at the surface of the crust, but we just have seen that material can get subducted and can reach mantle levels, or magmas from the mantle can intrude into the crust and then make the crust grow, because if you intrude magma from the mantle into the crust, it becomes part of the crust and the crust grows in size. The initial concept of this cyclic evolution of rocks comes from a man called James Hutton. James Hutton lived in the 18th century, and he was one of the first modern geologists who applied scientific methods to describe and analyze rocks and how they depend on each other, how they can convert from one into another. He was for his time a very brilliant scientist. I will leave that to your own study. Here is a lot of material presented again in a very complex diagram. Have a look at it. You might see here a plethora of different geological processes that we have mostly talked about in the previous lectures, from metamorphic processes, from deformation processes, glaciers that transport material, sedimentary environments, magmatic environments that we have discussed today. So here you see a lot of geological environments put together in a very nice, beautiful illustration. Have a look at that yourself. I just want to come back to this cyclic evolution of rocks with the sedimentary, metamorphic and igneous rocks and the interrelationships between these rocks. James Hutton, here he is again. That's when he lived, 1726 to 1797. What drives this cycle? What makes rocks increasing in depth? What brings them back to the surface? What brings material into conditions where they might undergo melting? The answer is this is plate tectonics. Plate tectonics is a kind of a very important umbrella concept that explains pretty much every geological process on planet Earth. There are very few processes that are not dependent on the mechanism of plate tectonics, and that's why we want to talk about plate tectonics at least in very principled terms. If you study geology, you will have something like 1.5 weeks of lectures just on plate tectonics. It is actually a very interesting but very complex mechanism that explains us how the Earth can change shape. Here we see two continents underlain by their lithospheric mantle, and these are, as we said, the mobile plates at the bottom of the lithosphere, here along that interface to the asthenosphere. That is a slip horizon where such continental plates or oceanic plates, like we see here, can laterally be mobilized. They can flow and migrate laterally in various directions. And if we see here one continent and here another continent separated by an ocean, like for instance Asia is separated from South America by the Pacific Ocean, we see here that the oceanic lithosphere can be subducted underneath a continental overriding lithosphere. As we have seen, this may trigger the partial melting of the asthenospheric mantle and produce a volcanic arc, such as the Andes, for instance. We also might have the situation of decompression melting, where melting occurs because mantle material rises very quickly, and also that might produce volcanoes, and that can happen either in oceanic or, as we see here, in continental lithosphere. We also can see that on the continents, wherever there are topographic high-lying areas and water and wind is available, that sediments can be transported. They can be transported all the way into oceanic basins or to the continental margins, where then large sedimentary basins might exist. These are important processes that play a role in plate tectonics. Decompression melting and water release from subduction zones are obviously spectacular processes, but they are not the only ones. The lateral mobility of lithospheric plates is the driving mechanism that, of which a lot of processes depends, secondary processes in geology. If we see that continents, as we see them here, can move together and consume oceanic lithosphere by subduction, then it's not surprising that at a certain stage the whole ocean will disappear and these two continents collide. We see that here in this diagram. Here we see that in between, in such a collision zone between continents, still remnants of the oceans are preserved. You see here all this bluish purplish material. This once was part of the oceanic lithosphere, and very often in continent collision environments we find remnants of oceanic material here, the dashed and hatched segments. This was formerly ocean, and that provides evidence. It provides evidence that once an ocean separated this continent on the right hand side, this one on the left hand side, which now have collided and have formed a large mountain belt. You see here this topographic high. This could be something like the Himalayas. The Himalayas have formed by the collision of India with Central Asia. In between India and Asia there was once a large oceanic basin which got subducted. You see here that such high mountain belts are undergoing erosion. You see here laterally on either side of such a large mountain belt sedimentary basins are forming, and they catch a lot of the material that gets eroded here from the high mountain ranges in the center. Uplift might support that. The more uplift occurs here, the better erosion will work, provided that rainfall assists this erosion effectively. With time, the mountains erode entirely, and deeper crustal material will get exposed, and this is how you find material that once was deep down in the crust can reach the surface, and that is where we can sample it and investigate it. Obviously, the erosion of such large mountain belts will create large sedimentary basins that we see laterally, because somewhere the material must go. And sedimentary basins, like for instance the Karoo Basin that we have visited on our little field trip, these are reservoirs where such sediment can be deposited. Eventually, continents also can break up again. We see here a situation of a continental rift. Rifts are large fractures in continents that precede the breakup of continents, and here in Africa we have a very famous one. The East African Rift is a mega structure. It's the largest rift structure on Earth today, where Africa is in the process of breaking up. Eastern Africa with Tanzania, Kenya, Somalia, parts of Ethiopia, and northernmost Mozambique are in the process of getting lost of the rest of Africa, and if this rifting, if this separation of the African continent will continue, then we might form eventually a new ocean along that line where we now find the East African Rift. You might know that along the East African Rift there is quite substantial volcanic activity in specifically the central part in Kenya. In Tanzania there are large volcanoes that are certainly known to you. The Mount Kenya, of course, the Kilimanjaro are the largest of them. So eventually Africa might actually fall apart. It might form two separate continents, with the so-called Somali plate and the African plate being separated. This is not yet quite so. We still have a coherent continent, but along the East African Rift we have a very thin asthenosphere, and decompression melting is occurring. That is feeding the volcanoes that we see at the surface. A new ocean might form, and in fact if you continue going along the East African Rift, you hit the Gulf of Aden and the Red Sea, and in the Red Sea there is already new oceanic crust forming, separating the African plate from the Arabian plate. In the not very distant geological past, this was one coherent continent. Arabia was part of Africa, but now the oceanic basin, the small and narrow oceanic basin of the Red Sea, is separating these two continental plates. So here we see this Wilson tectonic cycle that describes the fate of continents throughout the geological history. And since this is a cycle, we can actually start it wherever we like. Let's start it over here. Consolidated continent. That was my dog. a consolidated continent starts breaking up, like East Africa at the moment, forming a rift, an intracontinental rift where thinning occurs and where separation by sideward movements of parts of the continent occurs, and that can proceed to a situation where new oceanic lithosphere is formed in between, separating these fragments. This would be a situation where so-called passive continental margins form, a new oceanic lithosphere is formed along a mid-oceanic ridge involving decompression melting. Decompression melting has started here and initiated the rift formation. So this is a situation that we find in the Red Sea, for instance, today, or if you want to choose a larger oceanic basin in the Atlantic. We could say this here is Africa, this here is South America. 130 million years ago, the South Atlantic did not exist, and South America and Africa were forming one coherent large continent called Gondwana. Oceanic lithosphere doesn't exist forever. In fact, oceanic lithosphere never reaches an age older than 400–500 million years. And such oceanic lithosphere undergoes subduction, and this consumes oceanic basins. Oceanic basins can shrink as they can grow. And here we have a situation that we observe today in the Pacific, where the eastern Pacific plates are subducted underneath the Andes, underneath South Americas, destroying and shrinking the ocean, and eventually oceanic basins can get entirely consumed. Such a closure of an oceanic basin precedes continent collision. This is a situation that we see today in the Himalayas with for instance, the Indian plate having collided with Central Asia. This produces high mountain ranges like the Himalayas or the Alps, for instance, or many other mountain belts in the fossil geological record all over the world. And such high mountain belts, they will undergo erosion and consolidation. Erosion will form again such a consolidated, usually fairly flat, not topographically very high continent. Australia is such an example. It is entirely consolidated and has large areas that are almost free of topography. And again, such a consolidated continent can undergo the next cycle of the Wilson cycle and start becoming unstable and breaking up along a continental rift zone. This is the history of continents. Such an evolution has taken place on this planet for at least 2.5 billion years since the early Proterozoic. This was what I wanted to tell you about the rock cycle and the tectonic cycle. If you are able to describe in some logical form how rocks are recycled by erosion, by redeposition, by burial at higher temperature and pressure, they might become metamorphic rocks, they might undergo melting, this magma might come back to the surface, solidify, erode, become a new sediment. This would be the rock cycle. If you can describe that in some simple terms, I will be very happy. And I would be even more happy if you could also describe the Wilson tectonic cycle that describes the fate of continents. And this Wilson cycle directly or indirectly also is related to the cycle of rocks, because obviously if you form high mountain belts you will trigger erosion. Erosion will form new sedimentary basins. New sedimentary basins might get so thick that metamorphism starts at the bottom of such basins, and so on and so on. So if you get the principle, I will be very happy, and thank you very much for this lecture.